from the rotational motion, and the second one is also from a different type of like a pulley based, and both these questions are a good one for your IET examination. So let's start with the first one, and it states that a ring of mass m and radius r lies flat on frictionless horizontal table and is pivoted at a point on its rim about which it can rotate freely. A bug of mass, should be m, starts walking along the circumference of the ring with a constant speed v, beginning from the pivot point. Neglect friction between the ring and the table. Determine the angular velocity of the ring about the pivot. And we have to find out the velocity, angular velocity of the ring for two conditions. First condition is that when the bug has reached the point diametrically opposite the pivot, that is halfway around the ring, and second is when the bug returns to its pivot point. So we can just draw its approximate figure, and if we draw from its top side, so we are going to have a ring, and this ring will be free to rotate. Let us suppose this is our pivot point, and we call this as A, and this is center, let us call this as C, and the bug is initially at this pivot point. So this is the position of the bug, and this is our pivot point, and this position is our bug. Okay. And it is free to rotate about this pivot point. So we have to find out what will be the angular velocity of the ring when it is when the bug will be at the opposite end. Okay, so at this is the opposite end of the bug, and the second position will be the bug is at the same position from where it is started. So these are the two conditions about which we are going to find out its angular velocity. Okay. So let us assume that our center O, it is having coordinate 0, 0. Okay. And let us join these 2 points which are diametrically opposite. So this is A, and let us call this as point as A prime, which is diametrically opposite to it. Okay. So here we said that we have a center of the ring, and that center of ring is of O, and it is having a coordinate of 0, 0, and we considered a pivot point, and that pivot point is of A, and if we say that R is the radius, okay, and therefore we can write that the coordinate of A will be our r comma 0. And we are going to measure the angle with respect to this pivot point, that is A. And let us assume a general position of bug that is somewhere here, and let us call this position as C. Okay. So we assumed general position of bug, which is our C. And we are going to find out the angle of the bug which is relative to OA, and we assume that this angle, we call this as phi. So we can write that angle of bug relative to line OA, and this angle we called as phi. And therefore we can write that our from O to C, its coordinates can be written as r cos of phi and sine of phi. So now we can find out the bug position relative to point A, which is our pivot point. Bug position relative to pivot A. So it means we can just draw the triangle here. So O is our center, A is the pivot point, and we assume that C is the some arbitrary position of our bug. Then if we join from A to C, so we can say the vector from pivot point A to C, we can write that equation. So we can say that our vector from pivot A to bug C, we can write that R A to C will be equal to R O to C minus R O to A, and we simply substitute their coordinates. So we get our RAC will be equal to R, and this is our C. So we get this as our R cos of phi comma sine of phi minus R comma 0, and we can write that our R A to C will be equal to R, we can take as common, and this will be cos of phi minus R cos of phi minus R. So we are going to get this as a cos of phi minus 1, and second will be our sine of phi. So this gives us the bug's position vector relative to the pivot. This gives the position vector relative to the pivot. Now next we are going to find out the bug's velocity relative to the pivot. Bug's velocity relative to pivot. And as the ring is free to rotate about the pivot point, so if the bug starts to move, the ring is also going to rotate. Okay. So we have to find out the absolute velocity of the bug in the initial frame, and that will be with respect to two contributions. So you can say that the bug is walking along the rim of the ring. So because of that, the ring itself rotates. About pivot point, that is our A. Therefore, we can say the absolute velocity of the bug in the inertial frame comes from two contributions. First contribution will be ring rotation about pivot. Ring rotation about pivot. Let us call this as omega. Okay. So it means the whole ring is a rigid part, so it is going to rotate as a single entity. And the second contribution is bug's relative motion to the ring. Bug's relative motion to the ring. And let us call this as V. Therefore, we can write that absolute velocity of the bug relative to the pivot. Absolute velocity of the bug relative to pivot, or we can say relative to A. A is our pivot point. That will be equal to our velocity due to ring rotation plus velocity to the velocity due to bug walking along a ring. So we are going to have two types of velocities that will be contributing to the absolute velocity of the ring. First will be the ring rotation, and second will be the velocity with which the bug is walking. Next, we are going to find out what will be the angular rate of bug in the initial frame. Angular rate of bug in inertial frame. And basically we are going to find out, because we said our angle is our phi. Angle we have taken as phi. Okay. Therefore, we are going to find out rate of change of angle. Rate of change of angle, which we can write as phi single dot. Okay, that's first derivative. So let's find out what will be the angular speed of the bug walking along the ring, which we have said as v. Okay. And the velocity of the ring, or we can speed of the ring, speed of the bug will be in the tangential direction. Okay, because if this is the ring and bug is somewhere here and it is walking in this direction, okay, so that will be tangential speed, and let us suppose this is called as v, and this is center O, the position is A, and this radius is our r. Therefore, we can write that angular speed relative to the ring, angular speed relative to a ring, let us call this as omega relative, that will be equal to our tangential speed and radius, which is equal to v upon r. Therefore, from here we can say that our v, or let me write it separately, that our omega relative is equal to v upon r. Or from here we can also write that v is equal to r times omega relative. Next is the angular speed due to ring rotation. Angular speed due to ring rotation, and we wrote that its ring is rotating about the pivot point with the angular speed of omega. So we said that our ring rotates with the angular speed of omega. And therefore we can say that total angular rate of bug which we called as our phi 1 first derivative will be equal to a ring rotation plus its V upon R. So we can say that we got the absolute velocity of the bug is equal to, absolute angular rate of the bug is equal to over omega plus V upon R. And remember, this is our first derivative. Okay. So this is absolute angular rate. Absolute angular rate. And next we come to the moment of inertia. So first of all, we are going to find out ring's moment of inertia about the pivot point. So first will be our ring's moment of inertia about pivot. Okay. And this is our ring. Its radius is given as R. And we know that the moment of inertia of the ring about its center C, let's call this as our ICM, and we know that this ICM is equal to mr square, where m is the mass of the ring. And we are interested in finding about the pivot point A, so for that we are going to use parallel axis theorem. So we know that moment of inertia of ring about its center C, center is taken as O, about the center O, let us call this as ICM, and this is our m r square, where m is the mass of the ring. And we are interested in finding out about the pivot point A, and therefore we can use that from parallel axis theorem, we can write that moment of inertia of the ring about the pivot point A will be equal to moment of inertia about the center ICM plus md square. D here is R, so this comes as our R square. And we substitute our ICM, which is our mr square plus mr square, giving us 2mr square. Okay, so we got the moment of inertia. From here we can find out the ring's angular momentum about the pivot point A. Therefore we can say ring's angular momentum about pivot point A, that will be equal to moment of angular momentum of our ring, L ring, is equal to moment of inertia of the ring about point A multiplied by its velocity angular, that is omega. And from here we get that our angular momentum L ring will be equal to I ring about A is 2mr square multiplied by omega. Now we are going to find out the bug's angular momentum about pivot. Bug's angular momentum about A, that is pivot point. And for that we are going to use basic, that is our cross product. So you can say that from cross product, let us call this as L bug, will be equal to M, and we have this as R cross V. Okay, so obviously direction will be, because we had taken the ring setup in the XY plane, so direction will be in Z. And we can further write it as that our L bug will be equal to M times, this will be X V of Y minus Y and V of X. And we already know that our X coordinate is equal to our R cos of I minus 1, and our Y coordinate is our R sin of phi. And we can write that our velocity in x direction will be equal to minus R phi and its first derivative sin of phi, and in y direction it will be R dot phi, and we have this as cos of phi. Now we can find out the product. We are going to solve them separately. First of all, we are going to find out x vy, and then we are going to find out y vx, and then we can subtract them. So we have our first term, and that first term is x times v of y. So we get that our x is R cos of phi minus 1, and this comes as our minus R v of phi is plus, not minus, R phi dot cos of phi, and this will be giving us R square phi dot and cos of phi minus 1 times cos of phi. And now we come to the second term, second term is our y v of x, and y is our R sin of phi, and v of x is minus R phi dot and sin of phi. Therefore we get that our second term will be equal to minus, and we have this is r square phi dot and sine square phi. And now we can subtract them. So we get this as x v of y minus y v of x, and this is our, we can take r square phi, and we have here cos of phi minus 1 cos of phi minus and minus of r square phi dot and sine square phi, and we just expand and open it. So we can take this r square phi dot as common, so that will be r square phi dot. We multiply cos inside, so we get from here as cos square phi minus cos of phi, and this will be coming as plus sine square phi, and this cos square plus sine square is going to give us 1. So from here we get this as r square phi dot and 1 minus cos of phi. So we are going to substitute it in this equation. Let us call this equation number 1. So we can say from equation 1, we get our angular momentum of our bug will be equal to, we simply multiply it by mass, which is mass m, that is our r square phi dot, and we have this 1 minus cos of phi. Now we come to the final step, that is our conservation of angular momentum. Initially the bug was also at rest, as well as the ring was also rest. So therefore we can say that the initial angular momentum associated with the entire system, that is bug as well as ring, was equal to 0. Okay. So you can say conservation of angular momentum. Conservation of angular momentum. And like I said, that our ring was at rest and the bug was also at rest, so we can say our initial momentum was equal to 0. We can say that our initial angular momentum is equal to 0, and our final angular momentum is our momentum of a bug and plus the momentum of our ring. And the ring, we got it as 2mr square omega, and the bug we got it as mr square and first derivative minus cos of phi. Okay. So we can say final angular momentum will be equal to angular momentum of our bug plus angular momentum of our ring about pivot point A. So by conservation we can say that our angular momentum of the ring about the pivot point A plus angular momentum of our bug is equal to initial angular momentum, which was equal to 0. Now we substitute. Momentum of our ring was 2m r square times omega, plus bug was our mr square phi dot and 1 minus cos of phi is equal to 0. And obviously this r square cannot be equal to 0, so you can just remove this, and from this we get this as 2m omega plus m, and this phi dot is our omega plus v upon r, and 1 minus cos of phi is equal to 0. And we are going to solve it for omega because we are only interested in this omega. Okay. So we open it and try to sort it out. So we get this as our 2m omega plus m omega plus, okay, we have to multiply it by 1 minus cos of phi, 1 minus cos of phi plus m v upon r, 1 minus cos of phi is equal to 0. Now we can take omega is common from these two terms, so we get this omega, and we have 2m plus small m and 1 minus cos of phi, and we can take other part on our left side, right side rather, so this will be going minus, we have this as mv 1 minus cos of phi divided by r. Now it is, we simply multiply with the denominator, we get omega is equal to and the numerator we get this as minus mv 1 minus cos of phi, and in the denominator we get this as r times 2m plus small m and 1 minus cos of phi. So this is our formula of our angular velocity. Okay. And in this case, if you look closely, we have here a negative sign. Okay. Or here also we can make a conclusion that this is our ring and this v is our bug's velocity. Okay. And here is our negative sign. So in this case, what I assumed, okay, I assume that my bug is moving along in this direction and the rotation is along also in this direction. Okay, but because of this negative sign, my presumption was wrong, so the ring will be rotating in opposite direction. Okay, this negative sign tells us that information. So this is the only purpose of this negative sign. Now we come to our both questions. So in part 1 it states that the bug was initially at A position and we have to find out when the bug is diagrammatically opposite, that is A prime, and we assume that if this phi is the angle of the bug at a arbitrary position C, O is the center. So when the bug moves from A to A prime, this phi will be equal to pi. Okay, that is halfway point. Therefore, we can say that when bug is at A prime, we have our phi is equal to pi. So we substitute, and in this case we are, because phi is only with 1 minus cos of phi, so we get this 1 minus cos of phi, this will be 1 minus cos of pi, and cos pi is over minus 1, so this comes as 2. Therefore we can write that's angular velocity at point B will be equal to minus, and mass of the bug, its velocity, and this comes as our 2, and in the denominator we are going to r, and this comes as our 2m, and this will be also our 2 times small m. And this 2 we can cancel out throughout, so this will be equal to minus, and we have this as m times v, and this is a r, capital M and small m. Okay, so please remember this capital M is mass of the ring, and the small m is mass of bug. And we come to the part B, second part, and for part second it is asked that bug started from point A and it comes back to point A. Okay. So for that we can say that our value of our phi will be equal to 2 pi, because bug comes a full circle like this. And we are only interested in one term, that is 1 minus cos of phi. It gives us 1 minus cos of 2 pi, okay, and that will be equal to 0. Therefore the denominator term will be equal to 0, and giving us that phi of A will be equal to 0. So it means a ring come momentarily at rest as the bug reaches its to initial position. Okay. So we can say that the ring momentarily at rest, and from the first part we can say that a ring rotates opposite to the bug position because of this negative sign. Okay. So we can say a ring rotates opposite to bug motion. And according to physics it has to be true, because this bug is free to rotate, the ring is free to rotate. So as the bug is going to try to push move in the forward direction, it is going to push the ring in the opposite direction. So this has to be true. So in the starting I assume that they are moving in same direction, so that's why there was a negative sign in final. If we assume in the start also that they are moving in opposite direction, so this negative sign won't be there, but the entire formulation will be same. So this was the first question, and we come to the second question. And in the second question it states that it is a mixture of, you can say, Atwood machine and you can say equilibrium, so it states that a uniform beam is pivoted at point O. A mass m1 is suspended from one end of the beam at a distance L1 from the pivot. At the other end, a light frictionless pulley is attached at a distance L2 from the pivot, carrying two hanging masses m2 and m3, with m2 greater than m3 on either side of the pulley. Determine the relation among m1, m2, m3, L1 and L2 such that beam remain in equilibrium and has no tendency to rotate immediately after the system is released. Okay. So this is basically a rotation, but it is rotation in equilibrium. So entire system is equilibrium. So first of all, we are going to draw an approximate figure, and we are given that is a beam. So let us, so this is our beam, and there is a pivot point. So let us assume that this is our pivot point. Okay. And there are a mass m1 is somewhere here, and its distance is L1 from the pivot point. Let us call this as pivot point as P. And to the other end, we are frictionless pulley is attached, and to this frictionless pulley we have hung the mass m2 and m3. Okay. So it is said that m2 is greater than m3. So let us suppose this is our m2, and other end it will be our m3. So this is, and the distance of the pulley is L2 from the pivot point. So this is the basic figure of the question, and we have to find out the relationship between m1, m2, L1, L2 and m3. Okay. So first of all, let us try to solve this pulley structure. Okay. And so this is our, let me draw it. So P is our pivot point. Okay. So let me draw this pulley structure separately. And on the left side we are having m2, and on the right side we are having m3. Okay, and the string is continuous like this. Here also the string is continuous, and as string is continuous, so let us assume that the rotation T prime here as well as here. Okay. And m2 is greater than m3, so m2 will be moving in downward direction. And let us suppose it is moving in downward direction with the acceleration a, and m3 is going to rise upward direction with the acceleration a. And the downward force on m2, gravitational force acting on m2 will be equal to m2g, and similarly there will be m3g. Okay. And let us suppose that the tension in this string which is connected with this our beam is our T. Okay. And here pulley is fixed. Okay. So there is no movement on the pulley. Only its movement is that is going to free to rotate. Okay. So pulley is only free to rotate. The string are massless and inextensible, and the pulley is also considered as massless, and there is no friction anywhere. So these are the few conditions that should be mentioned in the question, but anyways it's not a big problem. Okay. So we can write the equation for our this pulley system. Okay. So we can say for m2, and M2 is moving in the downward direction. Therefore, we can say that our M2G minus T prime will be equal to M2A. And similarly, we can write for M3. So M3 we can write, it is moving upward direction. So we get our T prime minus M3G is equal to M3A. Okay. So let us call this equation number 1 and this as equation number 2. We simply add 1 and 2. 1 plus 2. T prime is going to cancel with each other, and we are going to get the equation as M2G minus M3G, and A we can take as common from the right side, M2 plus M3. And from here we can write that our acceleration A will be equal to M2 minus M3 times G divided by M2 plus M3. And we can use any of these equations, first or second, and we find out value of T. Or we can also do it otherwise also. Let us subtract equations and get the value of T, much more convenient. So we can subtracting first and second, and let me write it here. So we were having M2G minus T prime is equal to M2A, and we are having T prime minus M3G is equal to M3A. And if you subtract them, this will be minus and this will be plus and this will be minus. Okay, so we get this will be equal to our minus 2T prime, and this will be plus G we can take as common, and this will be M2 plus M3, and A we can take as common, so this will be coming as M2 minus M3. Therefore, we can say that our T prime or minus 2 prime will be equal to, let me substitute value of A, and A was our M2 minus M3 times G. So we have this as, one second, yeah, M2 minus M3 times G, M2 minus M3 and M2 plus M3. And this will be minus, this will become G M2 plus M3, and we can take it LCM, so G will have a common, and this will be coming as M2 minus M3 whole square minus M2 plus M3 whole square divided by m2 plus m3, and this is equal to minus 2t prime. So now it is a simple, we just open the bracket and g will be common, so this will be giving us m2 square plus m3 square plus twice m2 m3 minus, this will be over, sorry, this will be minus here, this will be minus m2 square minus m3 square and minus of twice m2 m3 and divided by m2 plus m3, and this is minus twice prime. These two terms cancel out and this will be coming as minus of 2, minus of 2 will be minus of 4, or we can say we just cancel out this minus sign, so this will be plus and this will be also plus, and it gives us that our t prime will be equal to twice m2 m3 times g and m2 plus m3. So we got the tension in the, you can say, lower beam, lower strings. Okay, so let me draw it here, and we said that at this tension is our t, and here tension is our t prime, and on the side also is our t prime. Therefore, from here we can simply write that our 2t, sorry, our t is equal to 2t prime. And now we come to our beam, so we can once again draw the beam. This is a point of pivot. L1 is the length on the one side, having a mass of m1. Okay. So this is mass of m1, and here there will be a force which is our tension T, and that is equal to 2t prime. And m1, it is going to exert in the downward direction m1g, okay, and this is our L2. So like it said that it should not be rotating, okay, so there is equilibrium in rotation. Therefore we can say that the net torque about the pivot point P should be equal to 0. So we can say that our net torque about pivot should be equal to 0. And for that there are two forces. One is our m1g, and it is at a distance of L1 from the pivot point, minus, and okay, second will be our 2t prime, or let me write it t, and that is at a distance of L2 should be equal to 0, because one will be our in clockwise, other one will be in counter clockwise. And if we substitute our t and t prime, so we get this as our m1g L1 minus 2t prime L2 is equal to 0, and we substitute our t prime. Therefore we get this will be equal to m1g L1 minus 2, and our t prime was our twice M2 M3 times G M2 plus M3 multiplied by L2 is equal to 0. And G we can take common because that cannot be equal to 0. Therefore, we get from here that our M1 L1 is equal to, this will be over 4 M2 M3 M2 plus M3 times L2. And we can just further solve it, otherwise we got the answer. So if we multiply by both this on the left side, we get this as our M1 M2 plus M3 times L1 is equal to 4 times M2 M3 times L2. So this is the relationship between M1, M2, M3, L1 and L2, so that the entire system is in equilibrium as soon as the masses are this M2 and M3 are free to fall. So this relationship is our between M1, M2, M3, L1 and L2. So these were the two important questions or concepts which are of your IIT mains as well as advanced also. First can be a suitable candidate for the advanced, and the second one might come in advance, or it is a suitable candidate for our mains. Okay, so this completes all the two questions. Thank you.